So as we look at our next problem, this is a problem that from the 2004 AP exam. We're going to be trying to construct a confidence interval, and we'll be talking about the same 4 steps that we've been dealing with the last couple days with long way confidence interval problems. Our first step in a confidence interval is the 3 P's: procedure, parameter, population. Our second step, 2 C's: check conditions. Step 3, this is where we carry out the procedure. And step 4, interpret results. As we read through this example, I'm going to highlight key phrases and key values that will eventually substitute into this long way answer to our problem. So let's start from the top. A pharmaceutical company has developed a new drug to reduce cholesterol. A regulatory agency will recommend the new drug for use if there is convincing evidence that the mean reduction in cholesterol level after 1 month of use is more than 20 milligrams per deciliter, because a mean reduction of this magnitude would be greater than the mean reduction for the current most widely used drug. The pharmaceutical company collected data by giving the new drug to a random sample of 50 people from the population of people with high cholesterol. The reduction in cholesterol level after 1 month of use was recorded for each individual in the sample, resulting in a sample mean reduction and standard deviation of 24 milligrams per deciliter and 15 milligrams per deciliter, respectively. The regulatory agency decides to use an interval estimate for the population mean reduction in cholesterol level for the new drug. Provide this 95% confidence interval. Be sure to interpret this interval. Step 1, procedure, parameter, and population. We now know 2 types of confidence intervals, a 1 sample Z interval and a 1 sample T interval. How do you know which one to use here? It depends on whether or not we know the population standard deviation. And in this problem, it says we have a sample mean reduction and standard deviation of 24 and 15. A sample mean and standard deviation. We don't know the population standard deviation. We know the sample standard deviation. That's S. That's this 15 value. Since we don't know the population standard deviation, we know the sample standard deviation. If we don't know the population standard deviation, use a 1 sample T interval. That's the procedure you're going to use here. So that's what we're going to start off by saying here is 1 sample T interval. Now we're going to discuss what our parameter is. Our parameter is still mu. Mu is the mean. The mean what? We said it several times. The mean reduction in cholesterol level. The population. Who's the population? Find the sample size first. It says the sample is 50 people from the population of people with high cholesterol. So if the sample is 50 people with high cholesterol, the population must be all people with high cholesterol. So we'll say that for the population. So in step 1, we've addressed the procedure we're using, 1 sample T interval, because we didn't know sigma. We knew S, but not sigma. So we use a 1 sample T interval. The parameter is mu, the mean something. Read the problem. They will talk about the mean something somewhere in the problem, and several times you see mean reduction in cholesterol level, so that's the parameter. Who's the population? Find the sample size and just replace the number with the word all. So if it's a random sample of 50 people with high cholesterol, the population is going to be all people with high cholesterol. Let's go to step 2, check conditions. We're going to use the same conditions that we did for the 1 sample Z interval. And the first condition we're going to check is to see if a random sample was taken. And in this circumstance, it does say in the problem, a random sample of 50 people from the population was taken. So our first condition is true, a random sample was taken. For our second condition, we either want our population to be approximately normally distributed, or we want there to be a large sample size, or we want to show that our sample data is approximately normal, and therefore we can assume that maybe the population is as well. It says nothing about normal in this problem. However, our sample size is 50, and since 30 is the cutoff for being large, we have met the cutoff. We do have a large sample size being taken. And usually we try to verify this by saying how big the sample size was. Here the sample was 50, that's clearly bigger than 30, so make sure that you write an inequality that states something to that effect. You can say 50 is greater than or equal to 30, or just 50 is greater than 30. Step 3, carry out the procedure. So we have our formula from the front side. We're going to use that formula here, x bar plus or minus t star times s over the square root of n. You don't have to rewrite the formula with symbols. If you immediately just want to substitute the numbers in, that's fine. Let's start with x bar first, our sample mean. It says sample mean reduction of 24 milligrams per deciliter. That's your x bar. Then we're going to have plus or minus. To find t star, we're going to go back to this table B, the same location that we found z star. But to find t star, it's a little bit different. They ask us to find a 95% confidence interval. So if we go back to our tables, we are going to go back to this 95% on the table. For t star values, what we're going to use are other values inside the table besides this last row. And we're going to use this column that says df. df stands for degrees of freedom. And degrees of freedom is a simple calculation that you can find by calculating n minus 1, the number of numbers in the sample size minus 1. We're using a sample size of 50 in this problem, so we're going to take 50 minus 1, which equals 49. And we're going to look up 49 on your table. Unfortunately, what you'll find is that the number 40 appears on the table, the number 50 appears on the table, but 49 does not. So what do we do if your degrees of freedom does not appear on the table? What we do is we actually always round down to the next smallest number. So despite the fact that 50 is a lot closer to 49 than 40 is, we always round down when working with degrees of freedom. So we'll use 40 degrees of freedom on the chart with our 95%. Since we can't look up 49 on the chart, we look up 40 degrees of freedom with 95% confidence, and what that corresponds with is a t star of approximately 2.021. That's the number we'll use in our formula. The S in our problem is 15. That's our sample standard deviation. N is 50. We'll plug those numbers in for S and N. And then similar to what we did for the one sample z interval, we'll substitute this in our calculator by crunching out both values. And for this we get 19.7. I'm going to go second enter on my calculator and replace the minus sign with a plus sign. This gives me my second answer of 28.287. We'll write both those numbers inside a set of parentheses, starting with the smaller number first, 19.7, and ending with the larger number second, 28.3 approximately. Our conclusion here is going to be very similar to what we had for the one sample z interval. We're going to talk about how confident we are. So we are using a 95% confidence interval here. So we are 95% confident that. Now we can talk about your parameter. The mean reduction in cholesterol level for all people with high cholesterol. If you want to include the population information, you can. At minimum, you have to talk about what we're estimating, which is always going to be your parameter, the mean reduction in cholesterol level. And then you bring up the two numbers we just addressed in step 3, is between 19.7 and 28.3. And if there's units to include, which we do have here, milligrams per deciliter, I think it's appropriate to include that as your conclusion. So when we're done, based on our sample mean of 24, we can be 95% confident that the mean reduction in cholesterol for all people with high cholesterol is between the two numbers we calculated. That's setting up a long way one sample t interval, again, very similar to what we did with the one sample z interval problem.